So up to this point we did some Bohr models and one example of a configuration. So, and we did it just for bromine. So, if we were going to do a configuration for xenon, you can't use that shortcut and just say xenon and think that's the correct answer. Okay? Okay, fair enough. So, how many of you think, with the limited time that we've dealt with these, like the shortcut method for the configuration? There is no shortcut for the Bohr model. Okay, so if we're going to do this shortcut for xenon, what must we start with? See? I just said that. Okay, because the next lowest noble gas then is number 36 in column 8. Yes. Okay. So remember, what block are the noble gases in? What block? The P block. How many columns are in the P block? Okay, and what period is krypton in the P block? It's in the fourth period. Okay, so one of the aspects, since we're not dealing with a D block element, remember, when you're dealing with the transition metals, you got to be a little careful. Why is that? Because you can't go by the periods on those unless you subtract 1. Okay? So in other words, scandium, element 21, is not 4D1. Okay? It's 3D1. Okay? And the periodic table does not tell you that, but your slide rule does. Okay, so all other elements, we can just start with the period that that noble gas is in, and you correctly said what? It's in the fourth one, so we begin with 5S2. Follow your slide. Okay. So this number, 36 plus your exponent, should be what? 54. Okay, so 36 plus 10 gives you 46. 48 and 6 more gives you 54. And that's what we're looking for. Okay? Is anybody lost up to this point? Okay? So, what about if we did the Bohr model for xenon? Maybe a little more difficult. Okay, we've got 54 in the nucleus. Follow your slide rule. Remember, when you're going down that slide, what are those big numbers telling you? The energy level in the period. Okay, so 1s2, then what? Keep going. Okay. Okay, now let's stop right there. Okay, where are we at right now? We've got a filled outer energy level. I bet we're up to krypton. Yep. So we are up to krypton. You add all these numbers together, we've got 36. Okay? So keep going down your slide. Okay? Okay. So notice the energy level we're in, first, second, third, fourth, fifth. We're in the 8th column of the 5th period. Okay? Well, look at your table, find the 5th period, go all the way across in the 8th column, and we find xenon. That's where it appropriately belongs. 5th noble gas, yes. Okay. But once we get a little heavier, okay, into lead, gets to be a little more tricky, but you've had exposure to this before. Okay? And notice, how are these the same? Now it's a little tricky when you look at that, but notice 1, 2, 3, 4, 5, 5th energy level, but it's not just the 5p, is it? It's the 5s2, the 5p6. Here they are right there, 5s2 and 5p6. Okay. We on the bus? All right. So, when we're dealing with lead, you tell me, you want to do the configuration for lead or the orbital, or excuse me, the Bohr model? The configuration, probably because that's easier, right? Okay, so what noble gas will we use? Okay, why not radon? Because what's the atomic number for radon? 86. Obviously, 86 is not smaller than 82. So we cannot utilize that for lead. So now, what period does xenon end in? We just showed that to you. Ends in the 5th energy level, the p block. So, following your slide rule, you're going to go 6s2, then way back to what? This is 5d10 or 4f14? 4f14, okay. I knew it was one of them two. Now I think you go back down to 5d10. But are we putting 24, 26? I think we overshot it, didn't we? Just a moment. 54. Okay, yeah. So we had just ended right here, 5d10. Yep, 3, 4, 5. Right now, we're on which element? Mercury. Okay? Is anyone confused with that and how we came up with Mercury? Because for one thing, if we look at our table, now again, we got to be a little careful when we're looking at these, okay? Don't just figure that this is the 4d10. No, that is not correct. Your slide rule tells you that this is the 3d10, the 4d10, and finally the 5d10. And that's where Mercury is, up to 80. Okay? So, we only have 2 left to go. So, what energy level are we in, or what period? There we go. My math was a little off earlier, should have known. Then when you add them two together, you're going to get 70. 10 more gives you 80, and 2 more gives you 82. And that's what we're looking for lead. Okay. That's probably why we're doing this last. We got to get the lead out. A little slow. You ever heard that, runners, before? Get the lead out. It's weighing you down. Yes. Maybe I'll say that tomorrow, cross country. Get the lead out.
Don't just stay and yell it.
Okay.
Keep this paper.
While they're running by, can't do that. It's got to be liquids. You could. I could do that. Which reminds me, the cross country shirts. How are they coming? Okay. Okay. Symbology, right? Okay. You ready? Doesn't this look fun? It's familiar. Perhaps you did some of that in physical science. You mean this? Sure, it's that doesn't. Oh, I bet you did. For lead? Yes, we're going to do the Bohr model. Does that answer your question? Okay, so now let's go ahead and do the Bohr model. Follow your slide rule. Okay? So we're going to do lead. You're going to need lots of space here. I don't think so. No. 1s2. Okay, what comes next? 2s2. Then, okay, 3s2. Okay? I'm just writing things up there. See? Oh, so now you're kind of taking a shortcut here, huh? That's what's throwing me off. Oh, yep, it should be on the fourth one. Yep. Now, one of the things, is this difficult to do? Well, maybe the first, second, or third times, but that's what's nice about having that slide rule. helps compensate for that, okay? So I think we got to put a 2 here. And then eventually we're going to have to put 1, 2, 3, 4, 5. Okay, so now we need what here? 5D, 10. Okay. And then finally, what? 6P. Yeah. There you go. And then again, if you add all these numbers together, you should come up with 82. Okay. Okay. Now, this is one of those aspects to where it's kind of an inside joke. It was during cross-country practice this morning. I always have them go a certain direction around the school. Okay? But I took a shortcut. So I ended up in front of this one. So I'm turning the corner, pumping my fist, saying I'm in the lead. Yeah, I kind of did. But then I told all the other students, didn't you see me? Or maybe just my molecules transferred. So that's one of the things we're going to learn later on this week. Is just boiled down to, is it Albert Einstein's spooky action on how electrons interact with one another? Or is it Niels Bohr electron entanglement? It is both. We really don't know for sure. Now, why is that important? We're going to start with small numbers. First of all, are we good with this material? If you can get all the way up here and no problems using your slide rule, you're going to be just fine. Okay? But when it comes... Wasn't it on... Probably on your sheet, though. But what I'm saying was on the back page of your handout was the vocab terms. Oh, well then there's probably extra terms on there and you don't use them. Would be my guess. Okay. So, back to this. We're going to do a very simple electron configuration to figure out what these is a... Yes. Yep. So it might help. I meant to say this before. You might want to grab a book, if you would, please. I know that's a lot of extra work. Yes. I don't know. That's no one from around here. No.
You know who all went to Coleman in high school in 09?
Yeah, that's it. Okay, so those textbooks are actually mine. Okay, they're mine. Yes. Yeah. Right, right. But no, I got the receipts back there. Those are from Amazon. So didn't like the curriculum they're doing here, so I'm familiar with that author. So purchased those. Okay, so what I want you to do is we're in chapter 4. Okay. So what we want you to do is turn to approximately page, I went past it. Okay, page 111, we discussed the configurations, okay, and when you turn to page 113, they're starting to show you what these orbitals really look like, okay, and how to do them. So, and your slide rules in your book on page 116, but we've copied that down already. And notice in the book they show you the different types of configurations, and they on page 117, that's table 4, okay, and they show you the shortcut method, but they keep going in numerical order. I don't like how that's done. It doesn't mean that it's wrong, it's just a different way of doing it, because to me, I think we should follow what the slide rule says. What I mean by that is look at page 118. In other words, table 5. When you look at whether it's scandium, element 21, or further down, okay, notice they put 3D1, then 4S2 next. Does everyone see where I'm at? Table 5, find the element scandium, SC, atomic number 21. But when you do the shortcut method, what does it say? You need to use argon, then what is next? 3D1, then 4S2. Now, that's how the author approaches that, but how did we instruct you to do that? Because what fills up first? What does your slide rule tell you? But what? No, which one fills up first? 4S. The 4S2 fills up first. So just be aware of that. That's what the AFABU principle is trying to tell you, the slide rule, whichever way you want to look at it. And I used to remember where it said that specifically in the book here. Okay, I'll have that information for you tomorrow. We can read that in the book, but someone go ahead and pick a number between 1 and 18. 17 is the first one that I heard. Okay. So, which element are we dealing with? Okay, so first of all, we'll do the configuration for that, because that's where this is derived from. In other words, that's where it comes from. But we're going to do it longhand. The configuration is a linear depiction. We do what? 1S, comma, 2p6, 3s2, 3p6. Oops. Okay. So here again, this is how you use this table. Chlorine is in which column? In the P block, which column? 5th. So that's what that's telling us right here. 3rd energy level, P block, 5th column. Okay? So, as we do this, now we're going to do what's called an orbital diagram, and it's derived from this. Okay. So what we want you to do, nope, little arrows. Yes.
It's nomenclature all over the next diagram works, but even on the structure pole.
Okay. I know it sounds like we're jumping around, but what I want you to do is look at page 108 now. Okay, so what we want you to do, okay, table 1, it says orbital letter designations according to the values of L, okay? Because when it comes to this, we're talking about orbitals and orbital diagrams, we're talking about quantum numbers, and there are 4 of them, okay? When we refer to quantum numbers, when you look further down on page 108, okay, what does it show you in green? It's a big heading. Magnetic quantum number, okay? And if you were to look back on page 107, it says principal what? Principal quantum number, angular quantum number, the magnetic quantum number, and it should be spin or spin quantum number. Okay, so we're going to assign the variables for these quantum numbers. Okay, so they are as follows: N, L, M, and S. So why they don't use P for this, I really don't know, because they're saying that's the fourth one, or excuse me, the first one, because the first one is the principal quantum number, then the angular momentum. So I don't know why it's not P and then A and then M. These two make sense, but these two it's a little different. Okay. This is going to seem really difficult to begin with, but I was trying to explain this to the freshmen, okay, when they're doing some of these physical science story problems. I say, just think of back in, you ladies, just think of back when you're in elementary, the first time that you were practicing doing serve with your volleyball. Chances are not every serve went over the net. Maybe they went into the net, maybe they went too far, maybe they went left, maybe they went right. It didn't mean that you couldn't do it. It just took a little extra practice maybe. And I'm willing to bet that at one point you might have thought, I'm just not going to get this down. This is mean to tell me I got to stand behind this line, step forward while throwing a ball up, keeping my eye on the ball, stepping forward with my other leg, bringing my other arm up, making contact, and make sure that it gets on the other side of the net. That's a lot of information for something that probably takes less than 0.3 of a second. Okay? Like I said, not that everyone stands with both legs right next to one another. Maybe you start maybe you take a step back, throw the ball up, step forward, and then like this, bring your arm up, follow through. When you think about it, it's difficult. But when you just go do it, it's pretty simple. If someone's describing that to you, you think, oh my God, I can't do this. Well, if we're describing this, that just looks like that is really, really over daunting. You say, this makes absolutely no sense. But when we approach it in this manner, okay, this will hopefully make a lot more sense, because we're only concerned about the valence electrons that ended up in the last energy level. So wherever we ended up, this is all we're concerned about, is right inside of there. Okay? This is why. When it comes to the letter N, that's where the energy level that it landed in. The last electron fell in which energy level? 3, or third. So we're going to put a 3 there. Okay? Then, when we look at the table 1 on page 108, it says orbital letter designation according to the values of L. So we need to do the value for L. The last electron fell in which one of those orbitals? S, P, D, or F? And this is where you get that information from. So when you find letter P on this table, what's the given value then for P? 1. Okay? So that information you can do without what we're going to do next. And that is each one of these, if it can hold 6 electrons, which the P block can, you can divide that by 2. You're going to come up with 3 blanks like this. Okay? And this is where it comes from. Okay? So we'll set that stage up. 1s. Now you can draw this information if you want, but this is the most critical way out here. Okay, so each one of these blanks can hold 2 electrons. And notice we need to get 17 of them. These arrows illustrate what electrons are. Okay, so if we got one pointing up, another one pointing down, there's 2 electrons, 1s2. So 1s2. S2, so here's our second energy level, S subshell. 1 up, 1 down. Notice that the P block can hold how many? And that's why there's 3 of them here, because each one of these lines can hold 2. 6 divided by 2, of course, gives you 3. So, this is where it's important, what we call the bus seat rule. Okay? Or Hund's rule. We'll read that a little bit tomorrow. Like, for instance, if you're climbing onto a bus that has 10 seats on it, and there are 15 strangers that don't know anything about anybody else, each seat can hold 2. So, human interaction, just the way it is, if you don't want to be with anybody else, remember there's 15 people and only 10 seats that can hold up to 20, which might mean that each one of those seats would be occupied by 1, then occupied by 2, because you don't want to sit next to a stranger, but at some point you don't have a choice. Okay, so that's why we call it the bus seat rule. Okay, so what that means is we've got 6 electrons, we've got 3 bus seats here. Okay, so when we're following that bus seat rule, we're going to start filling up an empty seat, another empty seat, then another empty seat. Now they don't have a choice. They need to start pairing up with one another. You might be thinking, well, why didn't we do that with the s orbitals? Well, there's only 2 to begin with. That's why. Okay? So now we've got these pointing up. We got 3 more to go. Now we start to pair up these electrons. Okay? We've got 2 in the 1s2. There they are. 2 in the 2s2. Okay? Here they are. The 2p6. 2, 4, and 6. Then the 3s2. Okay, now we want to follow your bus seat ruling, because if you don't, notice we're only going to put 5 of them in there, right? Because if you do that, 1, 2, 3, 4, 5, it just so happens that's still going to be right, but that's just luck more than anything else. Right. Okay. So remember, this is 3p5, because there's only 5 of them. 2, 4, and 5. This is the last electron that we're concerned about right there. Okay? So, how we deal with that is M equals a value of negative L to positive L. I'm putting capital letters here. This was a lowercase l. Now we're putting capital L's. Okay? So what was the value for L, which was what? 1. So what we mean by that, M then equals a value of negative 1 to positive 1 without skipping over 0. Okay, so we said L was 1, correct? Now, if you said, I am so confused, I get it. We're going to get better at this with practice. Okay? So M equals whatever the value of L was. Well, L was assigned as 1. So that means that the value for that goes from a negative L, or negative 1, to a value of positive 1. So we just put those values in up here. Negative 1 without skipping over 0, and then positive 1. Okay? So I'm not even going to ask if anyone's totally confused, because I'd be willing to bet that probably 4 of you individuals probably are. And that's okay at this point, because this is the very first time you've probably seen something this complex. Okay? So the reason I circled this, why do you suppose I circled that and there's a 0 here? What do you suppose I'm going to put in for M? 0. And then finally the spin is positive half or negative 1/2. It's going to be negative, because if it's pointing up, we say thumbs up. That's a positive 1/2. But if it's pointing down, we say boo. That's being negative. Boo. So that's negative 1/2. The letter or the value for S can only be positive half or negative 1/2. That's it. It can't be anything other than one of these two values. Okay? So, yes, wherever it falls into up here is what you're going to have for that value. It's either positive half or negative 1/2. So very quickly, if we read what they mean, now that we see an example, this may help with what the definition actually means. Principal quantum number on page 107. It says the principal quantum number, symbolized by N, indicates the main energy level occupied by the electron. So this was the main energy level occupied by that electron. So that's why N has a value of 3. It's the main energy level. Okay? So we're not going to go any further into that. Let's go to the angular momentum. Except at the first main energy level, orbitals of different shapes, known as subshells or sublevels, exist for a given value of n. The angular momentum, symbolized by L, okay, indicates the shape of the orbital. Okay? For a specific main energy level, the number of orbital shapes possible is equal to n. The values of L allowed are 0 and all positive integers less than or equal to n minus 1. Okay? So that's why we said you got to put 0 in there. Whatever value you associate with L, which can be 0, it can be 1, it can be 2, it can be 3. And if you're in the F block, you'd have negative 3, negative 2, negative 1, 0, positive 1, positive 2, positive 3. That is 7 lines. What's 7 times 2? How many columns are in the F block? 14. That's where we start putting these concepts together. We'll stop with that, and then we'll continue on with these two values tomorrow. Okay, I went on a little farther than I wanted to, but we will continue again with this tomorrow.